All right, so at the beginning of the section, we did mention that the reaction rate or the rate of a reaction can depend on several different factors, such as the concentration of the reactants, surface area, and one of the other things that we mentioned was the temperature dependence of the rate of a chemical reaction. So we know from experience, for example, we can recall this, that cooking, for example, happens faster at higher temperatures. Okay, so an egg boils faster at 100 degrees Celsius versus 80 degrees Celsius. Okay, so cooking goes faster at higher temperatures. At the same token, at the same token, why do we refrigerate things? Well, when we refrigerate things, refrigeration actually slows down the spoiling process, right? So it reduces or lowers the rate of that spoiling reaction. Increasing the temperature increases the rate of cooking, for example. So we know that from just intuition and also from general experience. What we're going to take a look at now in this section is we're going to quantify that using a chemical equation, and specifically what we're going to use, actually not a chemical equation, we're going to use a mathematical equation that's known as the Arrhenius equation. And this is going to relate and show us the relationship between the rate constant and temperature, right? So we have here K, the rate constant that we've talked about. We have A, and A is a new term that we're going to see. This is known as the collision frequency. You can think of it as how frequently the particles are colliding with each other. And then we have E raised to the power of the negative value of EA, and EA, remember, is the activation energy, and that's in kilojoules per mole is our unit. R is the gas constant, and the gas constant has units of 8.314 joules per mole Kelvin. And then T here is a temperature in Kelvin, or the absolute temperature, right? E again is just the base of the natural log. So a couple of things to note when we use the Arrhenius equation. We need to make sure that we use the correct value for R. So we saw R, the gas constant, back in the gases section in Gen Chem 1, and we used the value of 0.0821 liter atmosphere per mole Kelvin at the time. Now we're using a different value that has different units, and it's important that we keep track of the units when we use the Arrhenius equation. Now, as it looks right now, it may look slightly complicated. What we can do is we can rearrange this equation. We can do a little bit of math. We can massage it, if you will, and we can take the natural log of both sides. So I have K is equal to A times E raised to the power of the negative activation energy over R times T. So if I take the natural log, I have ln of K equals ln of all of this stuff, A to the E to the negative activation energy over RT. And if I rearrange this, so let's say, or we have ln natural log of K is equal to the natural log of A, and then minus activation energy over RT, right? So all we've done is simplified it. It may not seem simplified, but that's all that we did. And what we've done here now is we've tried to make it into a form that's a little bit more user-friendly. If we rearrange this, and this will sound like a common theme compared to some of the other things we've done previously, you rearrange this, I can end up with natural log of K being equal to, if I move this to the front, I have the negative value of EA over R times 1 over T. Okay, so if I multiply these two together, I get back this original thing up here. The EA times 1 is EA, R times T is RT, and that's the same thing as my negative sign. And then plus natural log of A. All right, so why did I do that? Well, when I rearrange that equation, guess what? I make it into a form that looks very similar to the equation of a straight line. Right, so I have my y value then being the natural log of K. I have my slope, M, being negative EA over R. My X value is going to be 1 over the absolute temperature. My Y-intercept is the natural log of A, that frequency factor. So that is going to be important because we can use that Arrhenius equation, rearrange it, and then if we plot a graph, we can approximate it to a straight line, and we can extract these values from a graph of experimental data. Right? So if we change some of the temperatures, we record some concentrations, record some times, etc., we can actually determine all of these parameters graphically. So let's take a look at an example of such a problem. So the rate constants for the reaction carbon monoxide, nitrogen dioxide, we measured at 4 different temperatures, right? So we have 288, 298, 308, 318 Kelvin, and we have our rate constants here. So what we're going to plot, right, Y value versus the X value. So if I have a set of axes, so on the Y value, I have natural log of K. On the X value, I have 1 over the absolute temperature in Kelvin. So I need to calculate these from the data provided. So I have the K value, I take the natural log of it, I get some numbers. I have the temperature, I take 1 over the temperature, I get these values, and I plot them on a graph. What I see is that I get actually a straight line, right? And that straight line is important because I can extract some of the parameters from there. So the slope, M, in my general equation for a straight line, which just vanished for a second, there it is. So if I get a graph or a line, right, the slope here is equal to negative EA, and a negative activation energy over R. So I would determine this from the graph itself. Right? I can then solve for the activation energy. So EA then would be equal to the negative value of the slope times R. And I can graphically determine what that hill or that barrier or that activation energy actually is. Now, in some cases, we can actually simplify our calculation a little bit. We have what's known as a 2-point form of the Arrhenius equation. I'm going to rewrite it so it's a little bit easier to interpret. We take the natural log of K1, so the rate constant under one condition versus compared to another. That's equal to the activation energy over R times 1 over the second temperature minus 1 over the initial temperature. So what this means is we really only need 2 data points to use this equation. And it allows us to do 2 things. If we know the rate constant at 2 different temperatures, right? So if we know this and if we know this at these 2 different temperatures, we can actually calculate the activation energy. Similarly, if we know the activation energy, if we know this value, and we know the rate constant, K1, at one particular temperature, we can actually, the value of the rate constant, we can determine the value of the rate constant K at any other temperature, right? So we can do a couple different things at least if we have this 2-point form of the Arrhenius equation. But again, we derived this and we didn't go through the derivation, but that's taking the original Arrhenius equation and then just substituting different values in there, first and the second value, and then rearranging it to solve it this way. So we have the original Arrhenius equation, we express it, we can rearrange it, manipulate it, whatever you want to call it, into a form that approximates to a straight line, and we can plot that data of ln K versus 1 over T. The slope is equal to the negative value of the activation energy over R. We can determine the activation energy from the graph. Similarly, with the 2-point form, we can solve for these different parameters as well. what you've been seeing so far in all of these examples is that, yes, there is some chemistry involved. Yes, this is a chemistry class, but if you take a step back, really this just boils down to a bunch of math that you're doing. A little bit of graphing, a little bit of algebra, you threw in a little bit of calculus and integration there, but you really weren't responsible for doing the integration, but just using the integrated rate law to solve for different things and to determine what those unknowns are.